For those of you who are not familiar with this seminar series, the Data Science Institute brings speakers of all academic domains to discuss relevant research and current topics in the field of data science. In the past, we've featured researchers from the NBA, Google, to Carnegie Mellon University, MIT, and Princeton. But tonight, we have the pleasure, I have the pleasure of introducing one of our own, Professor Suman Jana. He's one of our very amazing faculty members here at the Computer Science Department. And his primary research interests are in the areas of computer science, security, and privacy. And more specifically, he is interested in building automated tools for finding and fixing security and privacy vulnerabilities. He also delves into software engineering and operating systems. So without further ado, please give a round of applause for Professor Jana, and he will be speaking about securing software systems.
All right. Thanks, Mark. Thanks for the introduction. Can everybody hear me? Am I loud enough? Okay. All right. I'm Suman Jana. I am an assistant professor at DSI and Computer Science Department. Just joined last year in 2016 January, so fairly new here. And I work in, as Mark said, security and privacy, computer security. And the topic of today's talk is securing software systems beyond whack-a-mole. Okay, so let's begin. So I guess all of you probably know about this arcade game called whack-a-mole. It's just a mole shows up and you are supposed to hit the mole on its head, right? So it kind of shows up for a fixed duration and then it goes down, right? So the goal is to hit as many moles as possible. That's a popular game. And I talk about this, so you must be wondering, what's the context? Why am I talking about an arcade game? The context is that the state of current security practices essentially boils down to this. Okay, so what I'm talking about? Well, how do you make secure software systems? That's a fundamental question. That's the question that kind of drives my research. And I guess as a user, that's also very important to you, right? I mean, for example, if you have seen today's news articles about CIA breaking into different computers, leveraging Trojans, maintaining a cache of unknown security vulnerabilities so that they can, take over other computers, stuff like that, right? So the question is, well, why can't we build secure software? Like, why can't you do better as a community? So that's what I work about. And so in this talk, I'm going to give you a brief overview of why is it hard to secure software. So there has been some progress, but not as much as we would like. And I'll go through why it's fundamentally harder. Okay? And then talk about some possible future directions that people are pursuing and conclude there. So that's kind of the outline of the talk. And let's keep it informal. So if you have any questions, just stop me in the middle, ask questions, I'll answer. So that's kind of the setup. So let's talk about security whack-a-mole, right? So essentially nowadays, or rather, for existing software, the way we secure them is that we wait for somebody to break into the system. Okay, and then if you break in enough times, people will notice. There will be bad publicity, all sorts of stuff, and then you find out, well, let's see what is going on, what is wrong. Then you find out what is wrong, so you identify the root cause, and then the software developers are told by their corresponding managers that they need to fix these things because they're getting a lot of bad praise, so they need to fix these things. So they will try to fix as much as they can, and of course there is no check whether these fixes are also introducing further vulnerabilities, right? So you kind of just gather as much code as possible to kind of at least visibly fix this thing, and then you send it to the user. And I guess all of you are using computers, so you must have seen dialogues like this, right, coming up asking you, Microsoft has issued an important patch, or whoever, Apple has issued an important security patch. Do you want to install? Well, you don't get multiple options, so usually you just say yes, right? Or it gets automatically done in the background. The point is that this is the state of the art of computer security. Okay? And as you can imagine, this is not a good thing, right? Because essentially you are waiting to be broken into, right? And then you are trying to fix it. So essentially it's very reactive. And as we all know, reactive systems are not a good thing, right? So you want to be proactive. You want to kind of build the defenses before an attacker breaks in, before an attacker does something, right? So that's of course obvious. And before I go further, as you know, that this situation that most of the existing systems can be somewhat easily broken into basically leads to an arms race, right? As again, we probably saw in today's news about CIA, but essentially everybody is doing it. All the nations are doing it, and this is a very dangerous situation, right? So this is where they are leveraging these vulnerabilities, flaws in the software, to take control of the machine. Right. And as I said, this leads to a cyber arms race, right? And as we know from hopefully our previous experience with the other arms race, the nuclear arms race, this usually doesn't lead to good situations, right? So there has to be a more fundamental solution than simply making oneself stronger than the other. I mean, that's definitely a good thing in the short run, but in the long run, you want to be some sort of a more fundamental solution. Right. So, of course, I guess at this point, probably all of you are wondering, well, this is research, this is about science, so why can't just we have secure software? How hard can it be to creating secure software, right? And I get this question a lot. Several people who are not experts in computer security, who do other kind of stuff, come up to me and say, like, why is it hard? Like, are you guys not that smart, that bright? What is wrong with you guys? And the question, it essentially kind of stems from this fact that you hear about attacks on computers a lot, right? Compared to somebody breaking into a car or somebody blowing up a bridge, for example. So the idea, the essence of the question, I believe, is that we have learned how to build safe cars, safe bridges. Why not safe computer systems? What is fundamentally different? Of course, one answer is that computer science is a relatively new discipline, right, compared to civil or mechanical engineering. But I mean, that is one answer, definitely, and that's a valid answer. But I think that's not what it is. I mean, that's just part of the picture. There is something more, something fundamental that differs between like other systems and software systems. Okay. So, right, so let's first take a look at cars and bridges, okay, just to get the context, right? So, this is a picture, cars in 1930s, between cars now, and I guess there should be no doubt, right? We have made tremendous progress in terms of reliability of cars, right? These things do not break down randomly, engines do not catch fire, wheels hopefully do not come off, at random times. So there's no doubt. So there has been significant progress. Okay. The same thing applies for bridges as well. Again, we have secured them to the extent that a large number of people can walk on them. It doesn't break in. So it's all good. Okay. But if you think deep down, right, what is going on? So the question is, the point I will try to convince you is that this is not really safety. This is reliability. And reliability and safety are two different concepts. Okay? So the idea is that reliability means your whatever system you're building, it's reliable when there is no smart and adaptive attackers present. Okay? So that means it's reliable against naturally occurring events. So the thesis that I'm going to posit is that reliability is a subset of security. So in order for something to be secure, it has to be reliable. But it's not the other way around, in the sense that just because it's reliable doesn't mean it's secure. And the primary difference being the presence of a smart and adaptive adversary, like an attacker, who can probe things, who can replace things, who can kind of do smart things by knowing your defense. So that's kind of the key thesis here. So let's take a look. So as I said, reliability is not security, okay? And the primary reason is that reliability only requires your system to be robust against, as I said, commonly occurring inputs or conditions, right? So you can assume that there is a distribution of commonly occurring inputs and conditions, and you can defend, as long as you can defend against the most common ones, you will get high reliability, right? So even if you mishandle some of the corner cases, as long as they are rare, your reliability score will be very high, right? But the problem is that in case of security, that's not true. Because if there is an adaptive attacker, he or she will find out that these are the corner cases that you are not handling correctly. And they can force the system to go to those corner cases, right? And then you essentially, even though they are rare, the adversary can make them occur much more frequently, right? Assuming that they have control of the system. So that's kind of the fundamental difference. And as I said, this leads to my thesis that reliability is a necessary condition for security, but it is not a sufficient condition. Essentially, security is a much harder problem than reliability. Okay. So, and if you take a look, actually modern software is getting highly reliable. At least most of the critical modern software. For example, I don't know how many of you have heard of Amazon EC2. This is the cloud, one of the most popular cloud service providers. So Amazon has this service called EC2 where you can rent machines, virtual machines, where you can run your software, right? So this is what their SLA reads like. The SLA is the service level agreement that Amazon provides to the buyers, right? So if you are to go and buy a virtual machine or rent a virtual machine from Amazon, this is their guarantee. So the important part here, it has a bunch of text, but the important part here is that it talks about a monthly uptime percentage of at least 99.95, right? So that is their reliability guarantee. So if it doesn't happen, you actually get some money back. Well, not actually money, but you get some credit back, right? So that just shows that the fact that Amazon can sustain this business model shows that Amazon software is highly reliable, right? Because if they are not getting up to that percentage, they will lose a lot of money, right? So this shows that, and this is not just Amazon. This is true for pretty much all cloud providers. They can give these guarantees. But think about it. They can give these guarantees for reliability, but you'll never find any guarantee about security. Like, you'll never find a single line anywhere in any SLA saying that, if you get broken into more than 5 times a month, I will give you a refund back. Never, ever. Okay? That the reason, as I said, is that it's fundamentally a harder problem because the attacker can leverage different weaknesses, probe and leverage different weaknesses. Okay? So let's get back to the question that I started with, right? That cars and bridges, we have learned how to build these things in a safe manner. Why not software, right? So let me kind of reverse the situation here and say, well, let's see. So cars and bridges are definitely safer than what they were 100 years back, no doubt about that. But are they really secure? Okay, so what does it mean to be secure in that setting? Remember, security means there is an adversary whose goal, say, for example, is to destroy a car or a bridge, right? And he can have whatever resources he wants, right? In that model, is a car and a bridge safe? Of course not, right? That should be fairly obvious. So because the attacker can essentially probe the system and find out the weakest part of the system, right? And then cause it to fail. This is different from naturally occurring events because naturally occurring events follow a certain distribution that is not dependent on how the system is designed, right? So you can kind of design the system so that it kind of leverages that distribution. The attacker, on the other hand, is adaptive, so it can change depending on your design, whatever your weak part is. Okay. So quickly getting back to the car scenario, that of course the car is not secure, right? In this setting, for example, it should be obvious that cars can be destroyed fairly easily. All it requires is access to another dedicated car, right? Similarly for bridges, if you have heavy machinery, if you have explosives, it is not that hard to bring these things down. So if you put the same model, right, for software security as well as these things security, you will see that none of these things are secure. Okay? So the fundamental question at this point is, how can even we achieve security, right? Because if you do not know what you can trust, you'll always have insecure systems, like be it car, be it bridges, be it software. Because imagine whatever security mechanism you are building, that itself might have flaws, right? That itself might have components that do things in weird manner than you expect, right? So the fundamental question in security is, well, what are the trusted parts and what are the untrusted parts, right? So this is essentially what you call a threat model. So I'm going to make a very strong statement here, but it should be obvious from the discussion so far that no system, like it doesn't matter what system it is, like software, non-software, whatever, nothing can be secure if you just give an attacker unlimited resources, unlimited capabilities. So it just the nature of the game. So what can we do as security researchers? Because it seems pretty hopeless situation, right? So what we can do is we can limit the attacker into certain abilities, right? And the reason it's feasible in practice is because there is usually cost associated with attackers' resources, right? So that's why the goal is to build software, or any other system for that matter, that is secure against specific threat models. And threat models mean what the attacker can do, right? So for example, in a bridge, if you disallow an attacker physical access to the bridge, like physical proximity to the bridge, it's much easier to defend, right? I mean, of course, remotely blowing up a bridge might also be possible given the Internet of Things rage that's going on, but at least till now, the bridges are not connected, right? So if you can limit physical proximity with physical security, it'll be harder to blow. So that's kind of the bigger point here. So let's get back to the comment that I made earlier. So now hopefully I have convinced you that secure systems, building secure systems in general is hard, right? I mean, nothing is secure as long as there is a dedicated adaptive attacker, right? But that being said, I have to accept that you hear about software flaws, software being taken over, systems being compromised much more frequently than bridges being blown up or cars getting crashed willingly, right? So what is the difference? There is a difference. Like, even though there is no difference in terms of quality of security probably, but there is still a difference that is causing these things to be more frequent. Okay? So here is my hypothesis. The hypothesis is that it has to do with cost, and it has to do with certain nature of software. So the cost of launching an attack, okay, is much lower in software, especially in the connected world. So you can simply remotely probe a piece of software running in, even in another country, right, and get information about it. The same thing in case of cars and bridges are much higher. Most of them will require you to have physical access or to buy a car of the same model to kind of know what its weaknesses are. Here, your investment is really low, okay? And most of it doesn't require physical access, because as you all know, physical security is much easier to achieve because you can monitor who's coming in, who's going out. In the case of remote access, it is much trickier, okay? And then due to the nature of the design of software and the internet, right, there is usually no accountability. It's hard to track where an action is happening from, right? Who's triggering which packets. And again, this was by intention. I mean, these were intentional because, remember, internet was designed as DARPANET, where the goal was to sustain really drastic events like, like earthquake. Basically, the internet was designed so that it can survive even if pieces get, disconnected. And that, by design, didn't have any security mechanism because people thought it will not be used in the way it's used now, right? So that nature makes things even harder from the security perspective, because what you can do, you can send a packet over the network to probe a system, and then from the network's perspective, it will be very hard to trace back who actually sent that packet, because the internet doesn't have any built-in accountability mechanisms. And finally, software usually have richer set of functionality than bridges or cars, right? I mean, these things have usually a very narrow set of functionality. And when you talk about defense, when you talk about security, this is the key thing, because if you have a narrow set of functionality, distinguishing between bad function and good function is easier. In case of software, because the functionality is much richer, it's much harder. For example, let's say in a car, under no setting, a car's engine should be on fire, right? It's a very defined invariance, if you will, right? So if you have a system that always monitors a car and makes sure that it never gets on fire, it will have 0 false positives because, in real setting, it should never happen, right? On the other hand, as I will show in a second, that software bugs essentially do mimic users' actions, but without the user's permission. Now, this is a much trickier business, right? Because you cannot simply say this action shouldn't happen, right? You have to look at the context at which the action is happening, and you have to make sure whether this context is right. Like, this action is allowed in this context or not. So that's much subtler to check, and that's where a lot of the problems occur. Okay? So I'll go into the second part, but let me first check if you have any questions, because this is the second part where I'll sort of show why bugs happen and what kind of security bugs we're talking about, like why it's so bad. Yeah?
Just to remark, I see one of the things that I think to be important in that context is the incentive structure that you have when you build a car, when you build a bridge, and the regulatory environment of that. So if you have a software company, your main incentive is to make money as fast as possible, aka even if you know that there is a bug in there, which you will ship because otherwise you won't survive. And if you deal with the fallout later, you hope that the fallout is not going after your revenue. I think that's a major difference there.
That is true. That is absolutely true. Yeah, that's a very valid observation that, yes, so unless, in every system or in every economy, unless you are forced to do something, most profit-driven organization will do nothing, right? So right now, in software, there's not much regulation around software security, right? So the repercussions are really small. Like if something gets broken into or your software has flaws. So yes, that definitely is
This is a major point. If you want to have secure software, you have to have an incentive system that automatically drives people to do that. Otherwise, you can have a theoretical approach to that and say, okay, this is how you build a secure system, but nobody actually out there does it.
That is true. That is definitely true. Yeah. So that component has to be there. But I think in the current situation, we don't even have a theoretical way. So, but yes, you're right. Like both of these things have to work together in order for that ecosystem to change. Yes, absolutely. Any other questions? Yeah.
You mentioned the reliability of the Amazon software. Last week they had a major on S3 for several hours or a few hours, I guess, right?
That is true.
I heard that. It's almost scary.
That is true. That is absolutely true. So yeah, it turned out presumably that again they had some bug in their code, and there is this outage of a couple of hours, and I think again, so tying back to that theme is that they can get up to that 99.95 number because this couple of hour thing is like once in a year, right? Because you can make the average case good, but making the worst case good is much harder, right? Giving stronger guarantees about the worst case is much harder. So yes. Any other questions? Yep. All right. Okay. So let's move on. So the second part is about why are there bugs? Why is the software insecure, right? So of course, the reason is software bugs, okay? So you might have seen some of them. The Amazon outage was, of course, one example, but it was more of an availability thing. It didn't really cause some sort of compromise. But if you look at news articles, especially the technical sections, the bugs are dime a dozen. Like there are a lot of security bugs that come up all the time. Okay, so here are some samplings. So the more fundamental question is, why do bugs exist? Well, first of all, what are bugs, right? Bugs are behaviors or features in a piece of software that does not behave as expected. Okay, so I guess that is the generic definition of bugs. Well, so why do we have bugs? Well, it turns out that verifying that a piece of software will have desired behavior for all possible inputs, for all possible conditions is extremely hard. Basically, we don't have a way of doing this in a scalable manner. Like we have ways of doing this, but it only works for small pieces of code. It doesn't scale up to real software, like real world software. So that's the major problem. And remember that as long as there is even one condition, one input for which the bug can be triggered, yeah. Right.
So why do you say that it doesn't scale?
Right. So part of, well, first of all, of course, then you have, well, just for all of you, functional program is a paradigm. It's a different way of writing code, I guess. For this talk, I think that level should be good enough. So if you can definitely prove certain properties on functional programs, but you need to think of two things. One is what properties you are proving. Sometimes writing the properties themselves might not be as easy, like writing the specifications themselves. And second, people, of course, have to move to functional programming language. That's also another problem, but that's more of an usability thing. But more importantly, even for functional programs, large-scale proofs, like when you have large-scale software, it doesn't scale that well because all these problems fundamentally boils down to something which is called NP-complete. Basically, that means that there is no polynomial time algorithm for solving this problem. So as you increase the size, the overhead really increases very heavily. So that's the fundamental problem there. Like you can prove it for certain cases, but not for all cases. Does that answer your question, or if you have a follow-up question?
Yeah, I mean, I just wanted to know whether you had a practical experience with where this fails actually.
So for
So what was tried and where, how do you see and identify that this is happening? I mean, it looks like that there is some experience behind that doesn't scale.
Right.
It's not a theoretical statement, it's an actual statement that has been derived from some experience. So
Right.
what I'd like to know is how did that occur? What was the problem that you saw?
Right. So, right. So there are two things. I mean, I have something further down, along the talk, but just to answer very briefly. So, if you look at most of the theorem proving tools, so theorem proving tools are the tools that can, or formal verification tools are the tools given a property, given a program, it can verify things. Okay. But all of this essentially boils down, as I said, I mean, in most cases, to a problem, well, I'm kind of making simplifications here, but to a problem called satisfiability, okay? And satisfiability essentially is NP-complete. That means there is no algorithm for solving satisfiability in polynomial time over the input. That means it doesn't scale well, okay? So that's the fundamental problem. If you take... Mm-hmm. No. So the computational speed is definitely the issue. So as you go up the curve, you will cover more and more programs, right? But there is a fundamental difference between exponential time and polynomial time, right? So that gap is hard to bridge for larger programs. So the tools that are out there, what happens is if you throw the larger programs there, it simply times out. It never finishes. So that's the more fundamental problem, if you will. So I think we know that by nature it cannot scale. So that you have to have some compromises. Like that approach in itself will not scale to large programs. I mean, we can talk about it after the talk, maybe in more detail. But yeah, sorry. Any other questions? Yeah.
Just to comment on that, the main thing that slows is state-space explosion for a number of paths in the program take. So if you have a if statement, it has to say maybe that was taken, maybe it wasn't. If you have a loop, it has to say what if that ran 100 times, what if it ran 101 times, and so on. So spend most of the time proving how long loops run, whether it's taken or not, and on anything but a trivial program, that just explodes very quickly. So it is possible to write a proof, be very careful, very thin layers. So you say, here's the level at which I proved it, now I'm going to add like 2 functions and layer another level on top of that. And there was a paper at OSPI that just did this. They built a whole operating system like this. But it's incredibly painful. You end up with 10 times as much specification as you code.
If you just have something that doesn't necessarily depend on the state, I mean, that makes it way easier. I understand if you have something like written in C++ or PHP,
I mean, you have to define what correctly.
So let me say it this way. If you're willing, so you have, first of all, you have to define correctness. But more importantly, I think if you're willing to jump through a bunch of hoops okay, you can make reasonable sized software verify. But jumping through those hoops, as you were saying, is just too painful, and not everybody is going to do that. And even after that, it doesn't scale to large size systems. Like this OSDI paper, which is a premier conference in operating systems, basically showed that you can build a small file system, for example, that provably doesn't crash. Okay? But this file system is a really small system. A bunch of people at MIT spent like 2 years to build that. And there is no way, at least with the current technology, that it will scale up to a system where, say, for example, Linux file system will be verified, like the file systems that are supported in existing operating systems. So that's I guess is the bigger point, if that makes sense. All right. Okay. So getting back to my point is that so making correct behavior, ensuring that you have correct behavior. First, you have to specify what correct behavior is, but let's say you do that. Even then, verifying is a hard problem. And even after that, there is this notion of incrementality. So, things keep on changing really fast in software because you update the software. You add functionality. So the problem gets even worse, right? So now that you have verified a version, how do you verify the next version? So, and this happens pretty fast. So that's kind of the more fundamental problem. And let's take a look at how bugs become security vulnerabilities, right? Not all bugs are relevant for security vulnerabilities. Bug can be functional bugs. You have a program and you click something, it didn't work. So that's a bug, but it doesn't have any security implications, right? So let's look at a very common case called SQL injection, okay? So for those of you who don't know SQL is a query language which you use to read from a database. A database has a bunch of tables. You can say which field or which entry you want from that table through that query. And it's heavily used for web applications. So if you have web application, they usually cannot keep state. So all the state is stored in database. All they do is read from the database, send it out to the user, okay? So that's the idea. So let's say you have a web service which requires you to log in. And it's a very common setting, right? You need to log in pretty much nowadays for every web service. So this is the common setting. The user sends a username and a password. Hopefully your password is more secure than this, but this is just an example. So the idea is that once you send this, the web service will actually generate this query here to read from the database. Because remember, all the valid users and their passwords are stored in the database. Not in this form, it will be hashed for more security, but just for this simplified example. So this is, if you don't understand this query, that's fine. The key point here is there are these two fields which came from the user, right? So it just got replaced, and you're looking whether such a user exists, and if it does, whether the password indeed matches the password that the user provided, right? And if it exists, you say, well, login is successful, right? So this is the standard operation of the system. It works pretty fine. Life is good. Well, now, of course, if the login is successful, it's sent to the user, right? So now, let's say there is an attacker, okay? What it does, it actually sends these weird queries as username and password. Because remember, username and password is free-form strings. Anybody can put in whatever they want in there, right? Now, let's say this weird strings come in, right? So it's probably not obvious why this matters, right? So let's look at the query, what happens. Because remember, the program is blind. Whatever comes in, it puts it into the query, it checks, right? And remember, underneath, this is a language, right? The SQL queries is a full-fledged language. So once you put this thing in, again, I will not go into the technical details. The bigger point is this is a query which will always evaluate to true. Doesn't matter what you have in the database, right? And you can imagine why this is bad, right? Because that means that it will always say login successful, and the user will be able to do things without even knowing any password or username, right? So again, to tie it back to my theme, as I said, software security is hard because of functionality. Think of this, like somebody thought of this, providing this function that you can implement a lot. Yeah. Is that a question? Sorry. Okay. So I was just saying that because the underlying system is general purpose, you have to ensure that you are filtering out all the possible bad cases before letting outside data in and let it dictate the behavior of your program. So yeah.
Okay, so that was my objection.
Oh, the fact that, yeah. So
an open interface is in fact not fair because
That's true. But and in some cases, you have to keep the interface open. Remember, for example, like let's say, if you are a network service provider, right? Let's say you are running a server, right? You might want to provide your service to users who you do not know a priori, right? So you kind of have to let outside packets come in, but you have to filter the packets correctly so that they don't end up hurting your system. And that filtering is really hard. That's one of the point that I was making. So this is one example, and this is XKCD cartoon. I don't know if you have seen this, which basically makes this point about data cleaning before taking it in. Essentially, this is a mom who gets a call from her son's school saying that, did you really name your son this, right? And the son probably entered that as the name to the database. And those of you who might know SQL, this would basically drop the entire table. Like this is just clean up everything. So that's even worse than just logging in, right? So you have like really weird side effects. So the point is that whenever you take in data, you need to really make sure that you're doing this filtering right, and that's very hard. I mean, in the general case. So that's the point. Let's look at another example. So these are also very common example, a common type of bugs called buffer overflow. So those of you who have written code in C, C++, you will probably know that in C, C++, there is no memory management. In the sense, whatever object you create or whatever data you copy, you need to make sure that there is enough space in the memory for copying it over, right? You need to basically say, this thing cannot go beyond 50 bytes or whatever, like the limit, right? So that's the idea. So usually this works fine. You send an input, the input gets copied over, there is enough space, and things work fine. But again, remember, as the lesson should be from this talk, that there will always be an attacker who will try unconventional inputs, corner cases of inputs, right? So the attacker can try an input that is actually larger than the size of the buffer, right? So it will overflow some other data. Because remember, the input has a fixed buffer allocated to it, usually. And then if you don't check the length, you'll write past that buffer, corrupt other things that's after that buffer, right? I will not get into the technical details, but the summary is that essentially spatially crafted inputs can lead to execution of arbitrary code. And that's the holy grail of any attack, because leading to execution of arbitrary code means at that point as if you own the computer, because you can run any program on that computer, right? Essentially. So that this is really bad, and this is a very popular class of attacks. Again, it also shows you that simple mistakes can cascade into pretty devastating effects because of this corner case behaviors, right? So this is what a buffer overflow actual exploit will look like. So the key parts here is that there is a server running somewhere. In this case, it's the FTP server, which has a buffer overflow vulnerability. And remember, FTP servers are, they have to be open, right? Because somebody needs to log in and upload files or download files. Now, in this case, what will happen? It will send a spatially crafted input, and the attacker will get a shell here. And I don't know if you are familiar with shells. It's basically the place where you run commands. So once you get this, it's essentially you are as good as the actual user of that machine. You can do whatever the user can do, right? So at that point, the complete machine is compromised. There's nothing between the attacker and the machine. So, and this happens because that spatial input corrupted the FTP server, the program, right, that has buffer overflow vulnerability. And after that point, from the machine's perspective, it's as if the user is running all these commands, not the attacker. So that's kind of the key idea. Any questions? Okay. So these are some examples, and there are numerous like this. There are different classes. They're very common, very frequently happen. So of course, the question is, why are preventing these attacks hard? Okay, so it turns out that benign input and malicious inputs, separating them is actually a hard task, because if you can do that, then you can filter them out, right? So that will be the job of the data filtration, right at the input. But you cannot. So that's the problem. The input space of non-trivial real-world software is huge, and the malicious input, inputs that triggered bad behavior, can kind of be scattered all around it. So finding them is hard. Exploring them like one by one is not feasible because of the largeness of the state space. Okay? So one potential direction is automated bug finding, right? So as I said, verifying the software will be the holy grail, right? But given the problems with verification, and given that we fundamentally know that it will be very hard for it to scale to really large software, the another idea is, well, maybe we give up on complete guarantees. Instead of saying this is 100% secure, we have verified it, we say, well, we have tested it this amount of time with these tools. We have achieved a certain amount of coverage, in the sense we have seen a certain part of the input space, and we are reasonably confident. So that's kind of a compromise between scalability and what guarantee you get. So that's one of the potential directions, and that's what I work on. So the basic idea is you have code, you have specifications about the behavior, right? And you have these automated tools that's called bug finders, which will produce reports of potentially found bugs, and then you have to fix it, okay? So there are two questions here. One thing is, where will the specifications come from? Because describing the behavior of a program is also a hard task, right? So right now, people manually write it, but one of the direction that I'm working on is about automating mining of these specifications. How can you learn them automatically? Okay? The second is, what about false positives or false negatives here in this report, right? False positives means it might say that there are bugs here, but these bugs are not real. And that's not good, because then developers will end up wasting time, right? So you want to minimize false positives. And false negative means it might still have bugs that are not reported here. So you also want to minimize them as much as possible. If you minimize both of them, then you get verification. Because if there is no false positive, no false negative, then it is verification. But then, yeah. That is true. That is true. That is true. So you don't really specify the events. You specify the invariants that are the common case that should never be violated. And then you search for these events that might violate those things. So it's the other way around. But still, it's still hard, because you have to look for the events that are potentially can violate them, right? So you need a directional search. Then the question is, how do you decide the direction? Yes. But at least writing the specification is not specifying the events. It's specifying the common cases. Like, what are the conditions that should never get violated? For example, a buffer should never get overflowed, right? So it's the other way around in that sense.
In that sense, how do you define security then? Because if you only look through all things, there's obviously a problem. If somebody's smart enough to figure out in the specifications and some issue, or something that you specify that is undefined behavior, how do you deal with that issue?
Right, right. That's a very valid point. So your security will be as good as your specifications, yes. So if you miss something in the specification, you get nothing. Yeah, that's the current state. So, yeah.
What if the bug finder was corrupt?
Oh, the bug finder had bugs, right? Yeah, sure, yeah. So that's, again, one of those things, right? I talked about threat modeling. So yes, so you have to either, so remember, depending on the size of the bug finder, you might be able to prove some part of it, because it's hopefully is a smaller program than all possible software. But yeah, so you have to build in reasonable trust there, and you have to assume certain things about it. Yes, absolutely. Any other questions? All right. So the idea is that this automated bug finding will become part of your development process, right? So when you are doing regular testing, you will also integrate automated security testing as part of your regression test suite or continuous testing process. You will generate and apply fixes. Hopefully, soon enough, we'll also have auto-generated patches. May not be perfect patches, but at least good candidate patches. And then this will run in a cycle. So that's the hope, that's the goal. Now, there are several challenges, right, to build this system. The most fundamental challenge is something called Turing's halting problem. Okay? So for those of you who do not know what it is, it basically says, given a program and given an input, you cannot write, for all programs, right, you cannot write another program that can look at that program and say whether it will stop or not. So let me state that again. So basically, let's say there is a tool like Bug Finder. Okay, its goal is to prove, I mean not prove, but say certain things about properties of programs. Okay, one of the simplest properties is whether the program will stop or not. Right. So let's say there is a Bug Finder. It takes any arbitrary code as input, and you have an input to that code as well. Right. So given that input, the question is whether that code will stop or not. It's a very simple question. Right. What's Turing halting problem says, and Turing halting problem is undecidable in the sense that a Turing machine cannot answer this thing. Okay, but what it says that means is that there can be no single bug finder that can answer these questions for all programs. That's all it says. Okay, so we basically straight up we give up this thing that there will be no single bug finder that will find all kinds of bugs. Right, so that's essentially its implications. But that's fine. We are. I mean, I'm more of a practitioner than theoretician. You can say, well, fine. Sure, maybe not for all programs. Maybe for most popular programs. Maybe for more common programs. Because remember, all program the space is huge, right? So it might happen that developers don't write programs in that manner, right? So there is still some hope. But of course, you give up on absolute guarantees. So this brings us to the next problem that one of the answers we're referring to is that most code are not straight line code. So you have these if conditions in any code, right? So these things make it very hard to verify or trigger situations. Because remember, the buggy code there will not get triggered unless your input is a particular value, right? So that makes it much harder because you have to satisfy these constraints. And as you go deeper in the program, the number of constraints stack up, right? So you have to kind of satisfy all the previous constraints. So that makes it much harder to prove. And then finally, we also have this challenge about a large number of paths. Because in a real program, the software is large. So potential number of paths is really large. And if you have while loops or any sort of loop, it potentially is infinite because it depends on the data size, right? So as large the data is, the number of iterations will go on forever. So there's not much hope for exhaustive testing. And also, the rate of finding new paths, you can assume that, well, if the rate of finding new paths is somewhat linear with the resource you throw in, then it's just a matter of putting more resource in, right? That's also not true. Turns out for most of the constraints, as farther you go, the harder they become. So what happens is for any bug finding tool that's out there, you get this kind of plateau. After a point, it doesn't matter how much resource you throw in, it just flattens. So that just makes the problem even much harder, right? Beyond just simply throwing more resources at it. And finally, there is an asymmetry between the attacker and the defender, right? Because most likely they all have access to the same bug finding tools. The attacker just have to find one exploitable bug. The defender, well, it has to find all possible bugs. That just makes the thing even worse. So these are kind of all the challenges that we are facing right now. In terms of future directions, promising directions, there is at least one good thing that is coming up, which is similar to big data. We have now access to something called big code. Essentially, people are writing a lot of code. And that means that different people are making different kind of mistakes. And that gives us hope that you can infer some sort of specifications by comparing different programs. For example, GitHub is a popular repository where people put their open source code. And this is on the y-axis, you have in millions, the number of projects that are hosted in GitHub, and the x-axis is time. So if you can see, as you can see, the growth is really, really sharp, right? So it has reached 10 million projects hosted in 2013. So you have a lot of code that you can access, analyze, and compare from. So you don't have to analyze the code in isolation and find bugs. You can compare it with other programs, yes. That's true. That's true. So
what's the what's the argument that having more code as lines of code or
So it's mostly lines of code, yes. But the assumption is that they are developed independently because there is some sort of diversity in there. If all of them are suffering from similar bugs, right, then there is not much hope. If you make
Why can you assume that if you have many ways of expressing the same things and these different expressive things happen, why do you assume that this increases the occurrence of very rare events and decreases?
no, it does. Yeah, go on.
I think the argument is that when you develop, say you pick a code base, say Linux kernel, and you write the verifier against it, you've got a certain set of coding style standards and so forth. So there are crazy stunts you will not see because the Linux kernel culture does not allow it.
That's, yeah,
So the more with GitHub, and we don't have, we look at the open population of source, not the closed projects. The ability to suck in all the source being written gets you more language standards. So instead of, it's like, people the same argument as Watson. You digest Encyclopedia Britannica, you get the Encyclopedia Britannica style work. If you pull down the Wall Street Journal, the New York Times, the Chicago Tribune, Britannica, you get everybody's style work.
that's
Now you get to see, oh, they do this, that's above all.
that's an argument for the protocol and how you write software and whether this actually works in practice. And
So the assumption is that this software is mostly developed independently, right? So the assumption is that their styles are different, their natures of mistakes are different, the bugs that are in there are also different. So that gives you kind of a baseline to compare against, right? So you can kind of learn from these patterns and apply to other pieces of software. I guess that's the bigger point. Results in, so I didn't get your question, sorry. So you want to, you want to measure whether,
if you say that having these protocols and having these neural efforts writing how to write software in the right way,
right.
or at least in the way that reduces the number of bugs.
No, that's not the point that I'm making. The point I'm making is that, so it's not that each people are making less mistakes or making a communal, creating software in a communal manner is less bug prone. That's not what I'm saying. What I'm saying is if you have 5 different versions of similar functionality, chances are you will have different bugs in there. And then if you compare their behavior, remember, specifications was a major problem. How do you specify things, right? Here, what I'm saying, you don't need to know what the specification is. As long as you have different, the same functionality implemented in different way, you can compare their behavior across different inputs and conditions. And when they differ, you can say, there is something weird there. I mean, you can do other things as well, but that's one way of expressing the...
Question that maybe I formulated not in a way that's very understandable. It's more so you look into extremely rare events
Right.
bugs, hopefully it's at least.
Right.
You can exclude most of the things that are trivial by that, but if you're looking for actually security
Right.
vulnerabilities
Right.
anything like that, most of the time you have to dig a little bit deeper. You have to look for very specific things that go wrong.
Right.
So there should be some kind of critical threshold in terms of how many different versions of the software that does the same thing made by different people do you need to see very, very rare events happening in code.
So
My question would be, where is there a critical threshold has been met by
wow.
just statistically speaking,
The-
how more likely is it to see extremely rare events if you have just a few more samples?
Fair enough. No, so I don't have the exact data on that. The point that I guess, so when you say rare event, you are assuming that all the events are equally statistically probable, right? When we are doing testing, our hope is to trigger events that are more security relevant. So I didn't go into that detail, but there are already guidance process. We are not kind of triggering everything with equal probability. So there are already we are already picking events that are more likely to have security implications. But your question is perfectly valid, that once you raise the sample, how many samples do you need to get it to a significant value? No, I don't have an answer to that question yet, but I'm saying it's a promising direction.
Just my understanding, you have
100 databases. Depends on the actual distribution, right? So that's what I'm saying. Like if you assume that you are just testing naturally without any notion of where security relevant events might hide, right? Then of course, then there's no hope. But all I'm saying is there's already this sort of guidance built into these tools. The more samples definitely help it. Your question is whether, well, how much does it help? Whether it pushes it over a critical threshold or not. That is true. So the usual way to measure this is how many different events you cover, and this gets some sort of a number, but it's not a foolproof mechanism. Yes, you can have false sense of security. That is true in the worst case. Like you might happen to kind of only sample things that seem security relevant but not really buggy, right? Yeah, that can happen. Like there's no guarantees here. Like it's kind of a best effort thing. Maybe we can talk after that. Let me just finish this because. All right. So the point that I was trying to make, so this is the last slide. That if you are to leverage this big code, you can kind of leverage different patterns. For example, same developers often make similar mistakes, so you can kind of compare their code like for different functions and find those mistakes, learn from those patterns. The second point that I was making is multiple programs have similar functionality. As long as they're written independently, they might have different kind of bugs. So you can compare them against each other. You don't need spec to find these bugs. And finally, you can learn rules from past bug history because in the past, if the same project has similar kind of bugs, you might be able to leverage that as well. So that's kind of the end of my talk. So I guess if you have any questions, I will take your question in a second. But if you have any other questions, then I'm happy to answer. Yeah.
So can you give any specific examples of current state of art research or implementations? Sometimes bug finders along the directions you just described.
So these are very new. So these are all now research papers. There are not any production systems doing this thing. One of the production, at least open source system called CLE from Stanford has some of these features, but not these automated learning features. They are more manual. Like you have to give the specification, then you can kind of find different pieces. But most of this is very active research now, so it's not yet in any tools. But if you want like more pointers to the papers, I'm happy to give. Like just send me an email. Anything else? Yeah.
Will future computers be committing cyber warfare against each other?
That is a very interesting thought. I think they will, because the direction that we are going, automated bug finders can be, kind of just patched with an attack generation code, right? So yeah, I definitely think we'll see it in the future if we are not already seeing it. I don't know what NSA is doing, so. All right, that's all then. Thanks for coming, and I'll take your question in a sec.